The history of calculus is fraught with philosophical debates about the meaning and logical validity of fluxions or infinitesimal numbers. The standard way to resolve these debates is to define the operations of calculus using epsilon delta procedures rather than infinitesimals. Non-standard analysis instead reformulates the calculus using a logically rigorous notion of infinitesimal numbers. Non-standard analysis was originated in the early 1960s by the mathematician Abraham Robinson. He wrote, "The idea of infinitely small or infinitesimal quantities seems to appeal naturally to our intuition. At any rate, the use of infinitesimals was widespread during the formative stages of the differential and integral calculus." As for the objection that the distance between two distinct real numbers cannot be infinitely small, Gottfried Wilhelm Leibniz argued that the theory of infinitesimals implies the introduction of ideal numbers which might be infinitely small or infinitely large compared with the real numbers, but which were to possess the same properties as the latter. Robinson argued that this law of continuity of Leibniz's is a precursor of the transfer principle. Robinson continued, however, neither he nor his disciples and successors were able to give a rational development leading up to a system of this sort. As a result, the theory of infinitesimals gradually fell into disrepute and was replaced eventually by the classical theory of limits. Robinson continues, "It is shown in this book that Leibniz's ideas can be fully vindicated and that they lead to a novel and fruitful approach to classical analysis and to many other branches of mathematics. The key to our method is provided by the detailed analysis of the relation between mathematical languages and mathematical structures which lies at the bottom of contemporary model theory." In 1973, intuitionist Arend Hating praised non-standard analysis as a standard model of important mathematical research. Introduction. A non-zero element of an ordered field is infinitesimal if and only if its absolute value is smaller than any element of the form 4. A standard natural number. Ordered fields that have infinitesimal elements are also called non-Archimedean. More generally, non-standard analysis is any form of mathematics that relies on non-standard models and the transfer principle. A field which satisfies the transfer principle for real numbers is a hyperreal field, and non-standard real analysis uses these fields as non-standard models of the real numbers. Robinson's original approach was based on these non-standard models of the field of real numbers. His classic foundational book on the subject, Non-Standard Analysis, was published in 1966 and is still in print. On page 88, Robinson writes, "The existence of non-standard models of arithmetic was discovered by Thoralf Skolem. Skolem's method foreshadows the ultra-power construction. Several technical issues must be addressed to develop a calculus of infinitesimals. For example, it is not enough to construct an ordered field with infinitesimals." See the article on hyperreal numbers for a discussion of some of the relevant ideas. Basic definitions. In this section we outline one of the simplest approaches to defining a hyperreal field. Let be the field of real numbers, and let be the semi-ring of natural numbers. Denote by the set of sequences of real numbers. A field is defined as a suitable quotient of, as follows. Take a non-principal ultrafilter, in particular, contains the Francke filter. Consider a pair of sequences we say that in are equivalent if they coincide on a set of indices which is a member of the ultrafilter, or in formulas. The quotient of by the resulting equivalence relation is a hyperreal field, a situation summarized by the formula. Motivation. There are at least three reasons to consider non-standard analysis: historical, pedagogical, and technical. Historical. Much of the earliest development of the infinitesimal calculus by Newton and Leibniz was formulated using expressions such as infinitesimal number and vanishing quantity. As noted in the article on hyperreal numbers, these formulations were widely criticized by George Berkeley and others. It was a challenge to develop a consistent theory of analysis using infinitesimals, and the first person to do this in a satisfactory way was Abraham Robinson. In 1958, Kurt Schmieden and Detlef Lafwitz published an article, Eine Erweiterung der Infinitesimalrechnung, an extension of infinitesimal calculus, which proposed a construction of a ring containing infinitesimals. The ring was constructed from sequences of real numbers. Two sequences were considered equivalent if they differed only in a finite number of elements. Arithmetic operations were defined elementwise. However, the ring constructed in this way contains zero divisors and thus cannot be a field. Pedagogical H. Jerome Keisler, David Tall, and other educators maintain that the use of infinitesimals is more intuitive and more easily grasped by students than the so-called epsilon delta approach to analytic concepts. This approach can sometimes provide easier proofs of results than the corresponding epsilon delta formulation of the proof. Much of the simplification comes from applying very easy rules of non-standard arithmetic, as follows. Infinitesimal times bounded equals infinitesimal, infinitesimal plus infinitesimal equals infinitesimal, together with the transfer principle mentioned below. Another pedagogical application of non-standard analysis is Edward Nelson's treatment of the theory of stochastic processes. Some recent work has been done in analysis using concepts from non-standard analysis, particularly in investigating limiting processes of statistics and mathematical physics. Sergio Albaverio al. discussed some of these applications. Approaches to non-standard analysis. There are two very different approaches to non-standard analysis: the semantic or model-theoretic approach and the syntactic approach. Both these approaches apply to other areas of mathematics beyond analysis, including number theory, algebra and topology. Robinson's original formulation of non-standard analysis falls into the category of the semantic approach. As developed by him in his papers, it is based on studying models of a theory. Since Robinson's work first appeared, a simpler semantic approach has been developed using purely set-theoretic objects called superstructures. In this approach, a model of a theory is replaced by an object called a superstructure V over a set S. Starting from a superstructure V, one constructs another object *V using the ultra-power construction together with a mapping V*V that satisfies the transfer principle. The map * relates formal properties of V and *V. Moreover, it is possible to consider a simpler form of saturation called countable saturation. This simplified approach is also more suitable for use by mathematicians who are not specialists in model theory or logic. The syntactic approach requires much less logic and model theory to understand and use. This approach was developed in the mid-1970s by the mathematician Edward Nelson. Nelson introduced an entirely axiomatic formulation of non-standard analysis that he called internal set theory. IST is an extension of Zermelo-Fraenkel set theory in that, alongside the basic binary membership relation, it introduces a new unary predicate standard, which can be applied to elements of the mathematical universe together with some axioms for reasoning with this new predicate. Syntactic non-standard analysis requires a great deal of care in applying the principle of set formation, which mathematicians usually take for granted. As Nelson points out, a common fallacy in reasoning in IST is that of illegal set formation. For instance, there is no set in IST whose elements are precisely the standard integers. To avoid illegal set formation, one must only use predicates of ZFC to define subsets. Another example of the syntactic approach is the alternative set theory introduced by Vopenka, trying to find set theory axioms more compatible with the non-standard analysis than the axioms of ZF. Robinson's book. Abraham Robinson's book Non-Standard Analysis was published in 1966. Some of the topics developed in the book were already present in his 1961 article by the same title. In addition to containing the first full treatment of non-standard analysis, the book contains a detailed historical section where Robinson challenges some of the received opinions on the history of mathematics based on the pre-NSA perception of infinitesimals as inconsistent entities. Thus, Robinson challenges the idea that Augustin Louis Cauchy's sum theorem in Cause D analyze concerning the convergence of a series of continuous functions was incorrect, and proposes an infinitesimal-based interpretation of its hypothesis that results in a correct theorem. Invariant subspace problem. Abraham Robinson and Alan Bernstein used non-standard analysis to prove that every polynomially compact linear operator on a Hilbert space has an invariant subspace. Given an operator T on Hilbert space H, consider the orbit of a point V in H under the iterates of T. Applying Gram-Schmidt-1 obtains an orthonormal basis for H. Let be the corresponding nested sequence of coordinate subspaces of H. The matrix I, J expressing T with respect to is almost upper triangular, in the sense that the coefficients I plus 1, I are the only non-zero subdiagonal coefficients. Bernstein and Robinson show that if T is polynomially compact, then there is a hyperfinite index W such that the matrix coefficient or plus 1, W is infinitesimal. Next, consider the subspace HW of *H. If Y in HW has finite norm, then T is infinitely close to HW. Now let TW be the operator acting on HW, where PW is the orthogonal projection to HW. Denote by Q the polynomial such that Q is compact. The subspace HW is internal of hyperfinite dimension. By transferring up a triangularization of operators of finite-dimensional complex vector space, there is an internal orthonormal Hilbert space basis for HW where K runs from 1 to W, such that each of the corresponding k-dimensional subspaces Ek is T invariant. Denote by pi k the projection to the subspace Ek. For a non-zero vector x of finite norm in H, one can assume that Q is non-zero, or Q greater than 1 to fix ideas. Since Q is a compact operator, is infinitely close to Q and therefore one has also Q greater than 1. Now let J be the greatest index such that then the space of all standard elements infinitely close to EJ is the desired invariant subspace. Upon reading a preprint of the Bernstein-Robinson paper, Paul Halmos reinterpreted their proof using standard techniques. Both papers appeared back-to-back in the same issue of the Pacific Journal of Mathematics. Some of the ideas used in Halmos' proof reappeared many years later in Halmos' own work on quasi-triangular operators. Other applications. Other results were received along the line of reinterpreting or approving previously known results. Of particular interest is Kamé's proof of the individual ergodic theorem or van den Dries and Wilke's treatment of Gromov's theorem on groups of polynomial growth. Non-standard analysis was used by Larry Manevitz and Shmuel Weinberger to prove a result in algebraic topology. The real contributions of non-standard analysis lie, however, in the concepts and theorems that utilizes the new extended language of non-standard set theory. Among the list of new applications in mathematics there are new approaches to probability hydrodynamics, measure theory, non-smooth and harmonic analysis, etc. There are also applications of non-standard analysis to the theory of stochastic processes, particularly constructions of Brownian motion as random walks. Albavirio et al. Have an excellent introduction to this area of research. Applications to calculus as an application to mathematical education. Jerome Keisler wrote Elementary Calculus, an infinitesimal approach, covering non-standard calculus. It develops differential and integral calculus using the hyperreal numbers, which include infinitesimal elements. These applications of non-standard analysis depend on the existence of the standard part of a finite hyperreal R. The standard part of R, denoted street, is a standard real number infinitely close to R. One of the visualization devices Keisler uses is that of an imaginary infinite magnification microscope to distinguish points infinitely close together. Keisler's book is now out of print, but is freely available from his website. See references below. Critique. Despite the elegance and appeal of some aspects of non-standard analysis, criticisms have been voiced, as well, such as those by E. Bishop, Connis, and P. Halmos, as documented at Criticism of Non-Standard Analysis. Logical framework. Given any set S, the superstructure over a set S is the set V defined by the conditions. Thus the superstructure over S is obtained by starting from S and iterating the operation of adjoining the power set of S and taking the union of the resulting sequence. The superstructure over the real numbers includes a wealth of mathematical structures. For instance, it contains isomorphic copies of all separable metric spaces and metrizable topological vector spaces. Virtually all of mathematics that interests an analyst goes on within V. The working view of non-standard analysis is a set *R and a mapping *VV which satisfies some additional properties. To formulate these principles, we first state some definitions. A formula has bounded quantification if and only if the only quantifiers which occur in the formula have range restricted over sets. That is, are all of the form. For example, the formula has bounded quantification. The universally quantified variable x ranges over A. The existentially quantified variable y ranges over the power set of B. On the other hand, does not have bounded quantification because the quantification of y is unrestricted. Internal sets. A set X is internal if and only if X is an element of *K for some element A of V. *K itself is internal if A belongs to V. We now formulate the basic logical framework of non-standard analysis. Extension principle. The mapping asterisk is the identity on R. Transfer principle. For any formula P with bounded quantification and with free variables x1, xn, and for any elements a1 and a v, the following equivalence holds. Countable saturation. If Kn is a decreasing sequence of non-empty internal sets, with K ranging over the natural numbers, then one can show using ultraproducts that such a map asterisk exists. Elements of E are called standard. Elements of *R are called hyperreal numbers. First, consequences. The symbol *n denotes the non-standard natural numbers. By the extension principle, this is a superset of n. The set *n-n is non-empty. To see this, apply countable saturation to the sequence of internal sets. The sequence nn has a non-empty intersection, proving the result. We begin with some definitions. Hyperreals R, S are infinitely close if and only if a hyperreal R is infinitesimal if and only if it is infinitely close to 0. For example, if n is a hyperinteger, i.e., an element of *n-n, then 1, n is an infinitesimal. A hyperreal R is limited if and only if its absolute value is dominated by a standard integer. The limited hyperreals form a subring of *R containing the rails. In this ring, the infinitesimal hyperreals are an ideal. The set of limited hyperreals or the set of infinitesimal hyperreals are external subsets of E. What this means in practice is that bounded quantification, where the bound is an internal set, never ranges over these sets. Example: the plane with x and y ranging over *R is internal, and is a model of plane Euclidean geometry. The plane with x and y restricted to limited values is external, and in this limited plane the parallel postulate is violated. For example, any line passing through the point on the y-axis and having infinitesimal slope is parallel to the x-axis. Theorem. For any limited hyperreal R, there is a unique standard real denoted saint infinitely close to R. The mapping saint is a ring homomorphism from the ring of limited hyperreals to R. The mapping saint is also external. One way of thinking of the standard part of a hyperreal is in terms of dedecant cuts. Any limited hyperreal S defines a cut by considering the pair of sets where L is the set of standard rationals L(S), then S and U is the set of standard rationals B greater than S. The real number corresponding to can be seen to satisfy the condition of being the standard part of S. One intuitive characterization of continuity is as follows. Theorem: a real-valued function f on the interval a, b is continuous if and only if for every hyperreal x in the interval a, b, we have f*f. Similarly, theorem: a real-valued function f is differentiable at the real value x if and only if for every infinitesimal hyperreal number h, the value exists and is independent of h. In this case f is a real number and is the derivative of f at x. Kappa saturation. It is possible to improve the saturation by allowing collections of higher cardinality to be intersected. A model is kappa saturated if whenever is a collection of internal sets with the finite intersection property, and this is useful, for instance, in a topological space X, where we may want 2x saturation to ensure the intersection of a standard neighborhood base is non-empty. For any cardinal kappa, a kappa-saturated extension can be constructed. Bibliography.